Hi everyone, and welcome again. In this video, I want to continue the preliminary theory of higher order differential equations. This is part two. I already made a video on part one, so please watch that first. In the part one, I went over some notations, definitions, what's a homogeneous and non-homogeneous equation. So please make sure to know those before watching this part. So again, the preliminary theory is just the theory of higher order differential equations. And we're going to see basically that's the theory behind the higher order differential equations. And we're going to see how we can use this to solve higher order differential equations. And to solve it, the goal is to find a general solution. So what we're going to do is just go over some theorems, and then at the end, we're going to do some examples of solving it. With solving it, it's just a technique, but why those techniques exist, that's what we want to go over in this video. So what's the general solution? The general solution is a family of solutions. So remember, so defined in some interval I. So we know that we always solve a differential equation in some interval I, and that contains all the solutions of the given equations that are defined in I. So now to kind of go over that theory, let's go over a couple of definitions. The first one is initial value and boundary value problem. So let's understand what an initial value problem is. And we also call that IVP. Just watch the first video. If you see this, then that has to be automatic. Now this is nth order differential equations, and these are given initial values. Y of a constant is another constant, y0. Y prime of that same constant is y1, and so on, and it goes up to y to the power of n minus 1, so equals to yn minus 1. I have some graphs here for you that kind of explains the initial value problem, so and also the boundary conditions. So take a look at those, and it's going to give you graphically an idea. Now let's see. Let's start just with initial value problem of an nth order differential equation. What is this? We have an nth order differential equation, and this is not homogeneous. Equals to g of x. G of x is called the forcing function also. Now you are given some initial conditions, just I showed you just right now. Y of x0 equals to y0, and so on. The important thing here to understand here, it's an nth order differential equation, and how many initial conditions we have here, or we have to have here, they're all defined. So we have to start from 0 to n minus 1, and this is just n. So we need n initial conditions. If you have a second degree differential equations, then you need two initial conditions. Third degree, you need 3 initial conditions, and so on. And take a look at that graph too. These are for called the solution curves, which we saw in first order differential equations also. Now the main theorem here, it's existence and uniqueness. Existence, we want to know if a solution exists. And uniqueness, we want to know if that solution is unique. How can we check that? When you have a differential equation, nth degree differential equation like this, what you need to check if to see the existence of a unique solution. So first of all these functions, a sub n of x, they have to be continuous on the interval I, and also g of x has to be continuous. And if x equals to x0 at any point in this interval, then solution, then you have to have the boundary values for x equals to x0. If that exists, then the solution exists. That solution is unique. So you can double check this also, just for this specific differential third-degree differential equation. So you are given the initial conditions, and this is a homogeneous one, and those two are satisfied. These are, if I said these are functions, the coefficients, these are linear constant coefficients actually, so they're all continuous. So y equals to 0 is a unique solution, and it's called the trivial solution. Now the boundary value problem, sometimes if you're given, like this is a second degree differential equation, and you have two boundary values here, y of a equals to y0 and y of a equals to y1. So if you have that, then you can probably it's second degree come up with the solution, the unique solution. So let's see how we can do that. All you have to do is apply the boundary values. This is only for y. So if you apply them and solve here, y of 0 is 0. The first one, you get c1 equals to 0. And for the second one, you get y equals to c2 sine 4x. And if you apply the second boundary condition, so y of pi over 2 is 0, so you get c2 sine 2 pi. So we know sine 2 pi is 0, therefore you can say y equals to c2 sine 4x is this is satisfied for any value of c2, so you can use that. So this is going to be a solution for this equation for any value of c2. You can just pick a value for c2 and try it, and you'll see it's gonna work. So homogeneous and non-homogeneous equations, we went over this. The differential and operator notation, please watch my first video, and we went over this also on the first video. So the operator notation, again, we went over this also in the first video. What we are going to go over now is the theorem of superposition principle. What does that say? Let's say you have a differential equation and you solve it and you get all those solutions. So this is, and if you write this as a set notation, y1, y2, this is the fundamental, the set of fundamental solutions. Now, what does the superposition principle say? It says the general solution can be written as c1 y1x plus c2 y2x. So if you add all those solutions, it's still going to be a solution for that differential equation. So very important, remember that. Now, this is a good example. Let's say I have y1 equals to x squared and y2 equals to x squared ln x. So these are both solutions of the homogeneous linear differential equation, which is given here. Now, if I take the sum of these two solutions, c1 x squared 1 and c2 x squared ln x, this is also a solution of that differential equation. And you can try that. You have the function y, you can find the second derivative, the first derivative, and the second derivative, and the third derivative. And if you constitute, and you substitute, not constitute, in this equation, you are going to get 0 equals to 0, so it will work. Now you want to know if that's the general solution of that equation. So for that to know if it's general solution, you need to know if this x squared and x squared ln x are linearly independent. So for that, we're going to use the Wronskian, which I explained in the first video. That's very similar to linear algebra when two vectors are linearly dependent and independent. I do have a video on that, so please watch that video. It's going to make sense. You don't have to know everything, just have to know the meaning of linear dependence and independence. So if the solutions of you have a solution set, and if every member in that set are linearly independent, then you can say that's the general solution. So again, to check that, you have to do the Wronskian of the solution set. And if that's not equal to 0, then you can say they're linearly independent. So that's the general solution. I think we can, if I go over an example, that's going to make a lot of sense. So you can read these notes. And let's start from here. So the steps to solve an n-degree differential equation, what you need to do is find n solutions. So these are the fundamental solutions, y1, y2. And then second step is to check if they're linearly independent. So you calculate the Wronskian of that, and that has not, it has to be not equal to 0. So when that happens, they're linearly independent. So you can write the general solution as c1, y1 plus c2, y2 plus dot, 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 c and y. And then any linear combination of those is going to be a solution for that given differential equations. So this is a simple, a good example to understand how to solve it. If you have y double prime minus 9y equals to 0. So here the solutions are given, but let me tell you how we can find that. For an equation like that, you can write the characteristic equations, which is r squared minus 9. So it's r squared minus 9. For the double prime, you put r squared minus 9. So if it's y, you just put that equals to 0. You solve that equation, and I did that for you, get plus or minus 3. Now the solution of a homogeneous equation like that can be written as y equals to y sub I equals to e to the power of rx. And we have two r's here. One is -3 and the other one is positive 3. So I have my y1 and y2, which is given here. Next, we want to know if these are linearly independent. To the Wronskian, again, you put y1, y2, and here you take the derivative of the first one and the derivative of the second one. You evaluate or find the determinant. If you do that, you get -6. That's not equal to 0. Therefore, the general solution is written as c1 e to the power of 3x plus c2 e to the power of -3x. So, and to find the C1 and C2, you need the initial conditions or boundary conditions to find those. There's another example here. Find the general solution of, this is a third order differential, homogeneous differential equation. And just don't forget this work, the superposition work for the homogeneous nth order differential equation. So if I write the polynomial, you can write it like that. Now we have to put that equal to 0. Here I put a note for you just to refresh your memories of pre-calculus, how to solve an equation, third degree or fourth degree equations. When you cannot factor, you can use synthetic division. Here the leading coefficient is 1 and the constant coefficient is -6. So you take all the factors, possible factors of the constant coefficient, which are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and you take all possible factors of the leading coefficient, which is just plus or minus 1, and you find all the possible ratios, and these can be all the possible factors of solutions, all the possible solutions of this equation. How do you find that? Trial and error. You can use synthetic division. Synthetic division, and we try them one by one. I pick one here. So let me refresh your memories of synthetic division. So you write the coefficients 1, -6, 11, -6, and you bring this 1 down. 1 times 1 is 1. You write it here. Then you combine -6 plus 1 is -5. 1 times -5 is -5. So you get 6 here. 1 times 6 is 6. So you get 0. The remainder is 0. Therefore, r minus 1 is a factor. What's left these are the coefficients of that expression. So it's r squared minus 5r plus 6. So again, you can factor that, and this is easy to solve. The solutions that you get is 1, 2, and 3. That's why y1 is e to the power of 1x, y2 is e to the power of 2x, and y3 is e to the power of 3x. Next step, to Wronskian. So you take the first derivative and the second derivative of that, and so on for this. And if you solve that, you're gonna get 2e to the power of x, which is never 0. So then the general solution can be written as also homogeneous solution, like using the superposition principle, c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. Now, if you have a non-homogeneous equation, that's how it's written. Please watch the first video. And the general solution of a non-homogeneous one is the solution of the homogeneous equation plus a particular solution. Now here we're gonna kind of check. So if you have, this is the same differential equation in the last example. So if we have, we know that this is the homogeneous, the solution for the homogeneous equation. And if we have a particular solution, then I can say that the general solution is the homogeneous plus the particular, and write it like that. That's just, this example is just verified. Let's say you have 3 particular solutions. So the first one for the same equation. So, well, when I say same equation, it's not the coefficients are the same. So for this equation, you have that particular solution. For the second one, you have that particular solution. And for the third one, you have this particular solution. Now, what you can say, the particular solution of this equation, when you add all 3 of them, can be written as the sum of all particular solutions. So now in example number 13, so we are given a solution, so of that equation, and what we're given are the initial conditions. And again, the goal of this is, first of all, you can double check to see if it's a solution. So if you find the first derivative and the second derivative substitute, you get 0 equals to 0, so it's satisfied. Then to find C1 and C2, you can use the initial conditions, and you can come up with a system and then solve for C1 and C2. So that's going to be a solution of that differential equation. This is almost the same. So if you have a second degree differential equation, here equals to 12x. So this is not homogeneous. So you have some initial values, y of 0 equals to 4 and y prime of 0 equals to 1. And we understood that determinant has a unique solution, and we want to verify that this is a solution. So all the initial coefficients or of initial value problem, as well as the forcing function 12x, are continuous. So that's the first thing we check. Remember the existence and uniqueness term containing x equals to 0. So we know that a1 of x is not equal to 0. So the initial value problem has a unique solution at x equals to 0, because if you substitute, again, 0 is that number, so it's not 0. Then part B, if you want to verify it, verifying is now, we're very good at that. All you have to do is find the first derivative and the second derivative, substitute, and you get 0 equals to 0. So the given solution is a solution to the initial value, to the given initial value problem. And I think that's good enough for this video. Please watch it a couple of times And to solve the homework, it just you use the techniques and solving it, which is pretty easy. But that was the theory behind the nth order differential equations. Thank you for watching, and I'll see you in my next video. Have a good one, everyone.